Lesson 6 is the beginning of the place where you have to have a graphing calculator in order to do this. I put a link for a free 90-day trial of that calculator for your computer. So with that, remember, Lesson 6 is really more of the common, easy ways to present data. So what I'm going to do is I'm going to go over just a little bit of it, and then I'm going to have you work on the last couple just to get a little more practice.
I had a question about the homework. 21, when it was asking for the standard deviation on either side of the mean. Like, I understand what standard deviation is, but I didn't get the on either side of the mean.
Okay. Well, luckily, that was one aspect that I was planning on going over. So
Awesome.
So just sit tight for a minute, and I will show you what that means. All right, so first we're looking at a dot plot. A dot plot is really the simplest types of the displaying the quantitative data. We don't use it very often for big sets of data. We tend to use the dot plots for smaller sets. Statistics students took a survey of her friends to see how many semesters they've been at DVC, and she put the results in the dot plot below and used her dot plot to answer the following question. So this dot plot you see is X's, which is fine. We usually use dots, but it's still considered a dot plot. So what does each dot or X represent in the dot plot? So she surveyed her friends to see how many semesters they've been at DVC, and she put the results in this plot here. What does one X represent? So for example, what does this one dot here mean?
Student or one of her friends.
Exactly. So each one X represents one friend. Okay, so what does the placement mean? So for example, what does this X right here mean?
How many semesters they've been at DVC?
Yes, exactly. So she was here 6 semesters. Each dot represents how many semesters each one of her friends has been at DVC. So how many students are represented? That is to say, how many data points are there? And we always call that N. So how many friends did she survey? 6, exactly. Because there are 6 dots. I'll put dots in quotes because they're X's. So let's go to some definitions here. A lot of times they're going to be talking about the range of the data set. And you can see her friends have a range of between 1 and 6 semesters at DVC. In English, we might say her friends range of being here from 1 semester to 6 semesters, so 1 year to 3 years. But in statistics, range is a very specific calculation. When we say range, we don't want to know 1 to 6. We want to know the difference between those. So we do max minus min to get the range in statistics. So in number 4, we're asked to calculate the range. And you can see from that graph, the max was 6 and the min was 1. The max is 6 and the min is 1. So the range is 5. Then we also look at the mean, which in English, we refer to the mean as the average, but in statistics, when we say average, you may know, because I know a number of you have had statistics in the past, there are technically 3 averages in statistics: mean, median, and mode. But when most people say what's the average, they mean the mean. We're going to learn about the mean and the median. We're not going to be talking about the mode. We call that a measure of center because it is one way to talk about the average. What we really mean is what's kind of in the middle of the data set. You are going to need to know the statistical letters that we use to represent things. In statistics, we're using it's all Greek letters, okay? And we'll use uppercase and lowercase Greek letters, but mainly lowercase. The mean is the population parameter, and we use the Greek m, which is pronounced mu. So when we're trying to estimate the mean, what we're looking for is looking at this data set here. If we think about this data set being on a tray, and we think about each X being a can of food, where would you hold that tray so that the cans will all stay on it? Where would you put the fulcrum is the technical term. But where here would you hold the tray so that the cans don't all fall off? You see, we can't hold it here because then it will slide off the right side. We can't hold it here, then they'll slide off the left side. Do you see that we'd want to hold it somewhere in here to have things not fall off? So that's how we just kind of estimate And we're going to do that with the mean and the median a lot of times. Being able to eyeball it is a bit of a skill, but as long as what you're guessing is somewhere between 3 and 4, I call it good. I don't expect you to get the exact same answer that I am getting, but as long as you get something pretty similar, we're good. So we'll call this the mean, somewhere around 3 to 4, maybe a little closer to 3. So someone asked, could you put it at about 3.5? Yeah, absolutely. I would say it's most accurately around 3.5, somewhere in between there. It turns out it is exactly 3. So we'd say about 3.5. I'm going to skip ahead to the other set of dot plots we have. And that's an example 3. So in example 3, we're given the average temperatures of St. Louis on the top and San Francisco on the bottom. And this was the average temperatures per month. So you see down here is the data set. So they took the average temperature in January for both cities, February, March, etc. Then we made a dot plot. And you see the range. St. Louis is more spread out in temperature. And that makes sense because they have a much more harsher winter and typically a much hotter summer. San Francisco, our temperatures aren't as spread out. These were real temperatures that were taken, but it was about 10 years ago, which is why they're closer together and they're not reflective of what we would see in the last couple of years here. If we figure out the means, you see the averages, the means, which we denote X bar, the mean of a sample, and we say bar because it has a bar on the top. You see the means are pretty close together, but if you ask your friend, well, I'm traveling to St. Louis, what's the average temperature there? She said, well, it's 56 degrees. Does that help you figure out what to pack? No, because it depends on what month you're going there. If you're going to be going in December, it's 33 degrees. But if you're going in July, that's 80 degrees. So even though the mean is still 56 degrees, that average doesn't tell you much about each individual month. The San Francisco and St. Louis means being the same doesn't really tell you how to pack for each city. The mean doesn't give you enough information. That's when we have to branch out and look at another piece of information. And that's where the standard deviation comes in. The standard deviation is what illustrates this huge spread we see in St. Louis versus this compact bit we see in San Francisco. And when we figure out the standard deviation in our calculator, we put St. Louis in L1 and all of San Francisco in L2, and then we use the one variable stats. You're going to become very familiar with that. We're going to be using that a lot over the next couple weeks. The mean is here is X bar, okay, and then we have the standard deviations. And we have 2 different types of standard deviations. And you'll see they're pretty close together. And the one is the sample standard deviation, and the one is the population. We're not using the population standard deviation because everything we're going to be using for now is a sample. So we're going to take the S. We usually just say S, and this is the one place where we're using the English, the Arabic letter. For the population, we go back to the Greek, and we use the lowercase s. So they both mean S for standard deviation, but the actual S is for the sample, and the sigma is for the population. Now, this is not for our sample. This is for the X's we saw up above. So we see the standard deviation. I already did the work for the calculator. You see here's the means for both St. Louis and San Francisco and the standard deviation. And you see how much bigger the standard deviation is for St. Louis versus San Francisco. And so looking here for number 20, compare the range and the standard deviation for each city. The range for St. Louis, we'll call it 50 degrees, and the range for San Francisco was 11 degrees Fahrenheit. Compare these two and think about, well, how are these two related? Okay, and based on what I was just talking about, look at your paper, and if what you wrote down originally still kind of makes sense with what I was just saying. And if you didn't put anything there, think about how these two things are related. And it might help to go back and look at the dot plots as well. So I'll give you a moment to do that. Okay, so here, I'll show you what one standard deviation looks like. The mean is the X bar. Standard deviation is S of X. So I've written here the standard deviation for St. Louis and the mean for St. Louis. This is where colors really come in handy. So there's the mean. And we're going to go 1 or 2 standard deviations away. We want to see what's 1 standard deviation up from the mean and what's 1 standard deviation below from the mean. What that means is we're going from 56.1. I'm going to write 56, but we know it's more than that. And we're going to add 18.07. So 56 plus 18.07. And after we calculate that, we're going to go the other side and we're going to subtract 18.07. What that looks like then, we wind up at 74, which is here, and then we wind up at 38 over here. So going 1 standard deviation above gets us to 74, 1 standard deviation below gets us to 38. What we're going to learn later, lessons 13 or so, is that a lot of the data is within those 2 ranges. Most of the temperatures in St. Louis are between 38 and 74 degrees Fahrenheit. That's what the standard deviations tell us. And I'm just going to leave it at that for now. There's a lot more details we're going to learn later on. But that's the purpose of going 1 and 2 standard deviations above. And then we're going to do it a second time. From this 74, we're going to again add 18.07. And from this 38, we're going to subtract 18.07. We wind up at 20 degrees Fahrenheit, and over here, 92 degrees Fahrenheit. Almost all of the temperatures are between 20 and 92 in St. Louis. The reason why we like to go 2 out is because we can be more specific and say anything lower than 20 degrees and anything hotter than 92 degrees is rare. So rare we call it unusual. So this would be unusually cold on the left side, and then the right side would be unusually hot. So for the examples we have, the data we have, we don't have any temperatures that are unusually cold or unusually hot. Unusual is a technical statistical term. And like I said, for right now, that's all you need to know. Oh, although I will add one more thing. Anything that's unusual, we would call an outlier. I'll let you do the same thing with the San Francisco. I'm going to back up. We're going to do the same kind of idea, but we're going to do it with a different type of data. We're going to look at it with what's called a histogram. We switched to histograms instead of dot plots because if we had 10 years of data, trying to do a dot plot is a lot. Also, if we have data that's very spread out, trying to do a dot plot doesn't give us a good sense of what the data looks like. Okay, and we want to be able to have a better sense for what the data looks like when it's all compiled together. So what we do a lot of times is what's called a histogram, where instead of putting all the dots in one place on a number line, what we do instead is we create bins and we put the data in bins. With sometimes every 5, we put a bin every 5 units or every 10 units, depending on how much data we have and how spread out it is. Let's just back up to example 2. So for example 2, there's 50 items in the list. The range is 58 because if you hunt through or you put it in your calc, do sort A for ascending order, and we find the max is 97 and the min is 39, so the range is 58. And we want to put this into bin. I'm going to show you the quick way to do this, but I don't want to do that entire list. I just took the first column of the data. The best way to do this is to have the data set in one hand, this frequency list in the other. Frequency just means how many times does each bit occur. So I've got them sorted out, 35 to 39, 40 to 44. Each time a number in this range shows up, I'm going to put it into this bin here. Okay, so looking at this data set, I've got an 81. Don't try and find the total. Yeah, just do the hash marks and then find the total. So I got 81, I got 66, I got 43, I got 39, I got 92. I got 53, 88, 54. Okay, and we just keep doing that for all 50 things. I got a shortcut down here. I have the totals here. So there's the totals for the 50 sets of data. So when you add all these up, those will add to 50. And the relative frequency is relative to all the data, how many of them are in that first bin. Is this first bin has 1. Okay, so that's 1 out of 50. The second bin has 2 out of 50, 1 out of 50, 5 out of 50, 3 out of 50, etc. So that's the fraction. Now to write this in a decimal, where we divide. So the decimal is we take 1 divided by 50, and we get that decimal 0.02. 2 divided by 50 is 0.04. This is 0.02. 5 divided by 50 is 0.10, etc. And now what we need to find is the percentage. To get the percentage, you multiply the decimal by 100. So this is 2%, 4%, 2% again, etc. The decimal is what we use when we're talking statistics, but we don't think in terms of decimals. So if you're telling somebody or you're thinking about a problem, it's usually easier to write it in terms of a percentage. So what I like to say is that the decimals are statistics and the percentage is English. Because in order to make things make sense in your head, oftentimes you've got to translate them to your English. The percentage is how we think about it. The decimals are how we answer the question. Let's just finish this up. Sorry, I want to make the histogram. You see, I've put the totals of how many there are in each bin at the top here, just to make my life a little bit easier. And we want to fill this in at the end, but not right away. You want to do all the filling in later. So what I do is I just put the top. So here there's just one box, two boxes. See how I just put the caps on everything, and now I can go back and fill it in. Now I want to make sure we're clear that there's only one wall between the bins. So each box doesn't get its own wall, because that's if we have qualitative data like group 1, group 2, group 3, or hair color. That's when you have distinct boxes happening. In a histogram with quantitative data, this is a number line we have down here. And so there's only one wall between these because it's all one continuous set of data. To fill in the walls and then go back and just do a little bit of shading. You don't have to do a whole ton, but it's definitely a lot easier to see what's happening if you shade. So I'll just show you real quick what the rest of these looks like. You see in question 10, we've got this nice curve. Right, so on the top of page 6, we have an explanation for different shapes. So this one's a slightly left skew, and you see it's got more of a tail, right? The left is a little bit shorter than the right. So this would be a left skew. This is the shape, and you are going to need to know these different shapes. And the key for this bell-shaped symmetric is something we're going to be talking about a lot starting in lesson 13. The right skew and the left skew have to go with where the what we call the tail is, or where the shorter boxes are. So you see the shorter boxes are on the right as a kind of trailing off on the right, and that's why it's called a left tail. The tail trails off. Here the left skew, the left side kind of trails off. This one over here has two peaks, so we call it bimodal. And usually, oftentimes when you see these two peaks, it's because you're putting two different types of information into the same graph, okay? But this bell-shaped one is definitely our favorite. What I would like you to do, let's just do 23 and 24. These are in order from smallest to largest. And I put the answers here so that you can make sure that you're getting the same information out. A tip for what I do, I work down. So I put a 38. There's a 38. I've got an 81. Do you see how I'm using the boxes to kind of take that tally we were doing before? So I'm kind of killing two birds with one stone. That's kind of a more an efficient way you can do it. Use the boxes as the bins. Okay, and don't ever try and work across a data set. The longer the data set is, the more likely you are to get lost within it. Make the boxes and then use that to try and do the two standard deviations on each side of the mean, like we had done with the data in St. Louis. I'll show you what I had.
I have a question.
Yes.
Or a note. When I was counting the 90 through 99, I had counted 8 instead of 7.
Thank you. You're absolutely right. Good catch. So this should be 8. Speaking of that, anytime anything you find is confusing or you're unclear about it, please do let me know, because either I'm wrong and I want to correct it, or I'm not wrong and I want to make sure you understand why. Hopefully this is what you got too, yeah? And so notice I have the mean of 76, so I put this here, and then I go roughly 17 on either side. So I add 17 to get to 93, and then add 17 again to get to 110, subtract 17 to get to 59, subtract 17 to get to roughly 42. Looking here then, remember the whole reason we do this is to find unusual and to find where most of the data is. And remember, so most of the data is here. And does that look truthy? Do you believe that? Yeah, that looks pretty good based on my histogram. That looks truthy. Remember, the 2 standard deviations away tells us where it's unusual. And I always get stuck on how to spell unusual. I have to think about it. I get lost in all the U's and N's. So those are unusual. Do we have any unusual data points here? Indeed, we do, because there's one here is 38. That's unusual. Now here I have a 43, and it looks like I might, but when you go up here, you see it's actually a 44, so it's not unusual. So we have one unusual point, 38. In practice, that's probably one of the most common uses of standard deviation, to determine where most of the data is, what range most of the data lies between, and to figure out if there's any unusual point. Remember, these solutions are all on Canvas. And remember, I'm going to stick around for the next 20 minutes if anyone has any further questions. Tomorrow, we're going to look at a different way to present data. Sometimes histograms don't tell us the whole story, right? We use a histogram because a dot plot isn't good enough. But if the histogram isn't good enough and we want to learn a little bit more about where most of the data lies, we go into what's called a box plot. And that box plot is what we're going to be talking about tomorrow, also known as box and whiskers, because there's two little whiskers that come off of the box. All right, with that, have a great afternoon. And don't forget, I'll be around for 20 more minutes. If you have questions, just stick around. Other than that, have a great weekend.